Okay. Well, good morning. This is Chris Alexander. We're trying we called an audible at the last minute. We're doing live stream. So if you're on the WebEx, if you want to get the optimum audio, we did get a message from one of the operators said that the YouTube is blocked. So that may not be the best option. But anyway, I've got my laptop sitting here, but if you can do the live stream, that's probably the best option available. We appreciate you being with us. We understand that you are all working from home. I'm actually in our ice cream shop in our house. We've got a room that kind of looks like a 1920s ice cream shop. This is not really ice cream. It's from fakefoods.com, but appreciate you being with us today. Most of you that know me know I love testing stuff, and I've always been that way. Even in graduate school when I was at A&M, really enjoyed testing things and trying to make sure things work. And so what we decided to do, Chantz and I have been talking about this for a long time, and it just seemed like a great time just to kind of get everybody together. We realize that most of you are working from home, and just spend an hour today talking about things. I do have the WebEx up, so if you want to try to send some messages to us, that might work. Let's see. Also, if you wouldn't mind, if you could mute your, we've got probably 60 or 70 people calling on. If you could mute your speakers and not mute your speakers, but mute your microphone, it'll make it more pleasurable for everybody else. So we're obviously here to talk about full-scale testing. And kind of how we're going to kind of run through this is I'm going to open with a few deep thoughts. Those of you that know me know I'm a little bit sarcastic. I have to kind of watch that here at home. Going to talk to you about a concept that we have called ICAD and kind of how testing can work with integrity management. We're going to spend a lot of time talking about what are the goals in testing and really trying to help you understand how testing as an operator can really work with you in your integrity management efforts. Most of you on the call today are operators. That was intentional. We've got a call this afternoon, so today's kind of operator day. Next week we'll probably open it up to a lot of technology companies and probably have a larger group. Also, this live stream thing I'm hoping is working. Because it'll allow us to reach a larger audience. And so my daughter Ashley, who's at A&M, is manning the booth for us today, and if it wasn't for her, we wouldn't be able to do this. Because you all can't come out to Waller and see us, we're having a simulated lab tour, and so I've got some photos of some of the things that we're doing. And we've got guys working today doing testing and repairing samples and those kind of things. So one of the things I like whenever I present is to talk about case studies, and sometimes we call them war stories. And we'll talk a little bit. I've got 4 of them. I could talk for hours. Those of you that know me, we lost our screen there. Uh-oh. So those of you who are on WebEx, we're still doing. We're having a little technical difficulty here. I'm not quite sure what to do, Ash. So just a second while we get Microsoft Display Adapter working here. Wireless display. Okay, we're back. Okay, here we go. Boy, it used to be easier in the days when we just had transparencies. So why are we going to talk about testing today? And I thought I'd just kind of take an opportunity to kind of have a monologue and visit with you about why do we do testing. And I started working in 1993, a long time ago, 27 years ago. And so my wife Tanya and I were finishing up school at A&M and looking for a job. And it's amazing what happens in a 27-year period, the things you get exposed to. And so kind of throughout my career, I've spent a lot of time running models. Early on, spent a lot of time doing finite element modeling. Huge fan of that. If you watch the news at all, and I think we do, you hear a lot of term about modeling and talking about the flatness of this curve. And what I find really ironic as an engineer is we have a lot of people talking about modeling that, 6 months ago, they didn't even know what a model was. So when you got a lot of people who are not scientists talking about models, I've been so tempted to call in and ask somebody a question, but those of us who are engineers, we live our lives modeling. And so we make an assumption about how something's going to perform. And one of the interesting things when you do testing is you find out if the models are right or wrong. Sometimes the models are spot on, but sometimes the models are way off. And so the beauty when we go to the test lab, we can make some assumptions about how a pipe's going to perform with a dent or a crack or corrosion. We can model that, but when we go to the lab, we can really see what the result's going to be. And so that's why I wanted to talk about testing with you today. A lot of you on the call I've worked with over the years, and many of you even now we're working with you on testing projects. So I like to read. If I had 48 hours in a day, I'd read for 24 of them. And Wendy Courtwright, that a lot of you know, Wendy got me this book for Christmas, and our whole company read it. It's called Shut Up and Listen, and it's from Tillman Fertitta. And if you know anything about Tillman, he lives here in Houston. He owns the Rockets. He owns casinos, lots of restaurants. He's been unbelievably successful. I don't envy the position that he's in right now. It's a difficult time, especially for people who own restaurants. But I got a couple of deep thoughts. And the first one that I have is all models are wrong, but some are useful. I didn't make any of these up, so if you don't like them, don't blame me. But in the context of what we're talking about today, it's always good to assume the model is wrong until proven otherwise. And so that's a lot of what surrounds full-scale testing. The second one is give that to Ronald Reagan. He might not have made it up, but he certainly is widely recognized as one who used it. And it's the concept of trust but verify. And I tend to be a very trusting person. I'm optimistic as my natural bent. But in the engineering world, you got to verify that things work. One of the things we're going to talk about a little bit today is we're going to talk about technologies. And I'll admit, I'm an engineer. I've got 3 degrees in mechanical engineering, but I'm a little bit of a sales guy. And one of the tendencies that salespeople have is a propensity to oversell things, is a tendency to say that they can do better than they really are. It's kind of like I went to A&M, and it's easy to talk about how great the Aggie football team is until the season gets about halfway through, and then reality sets in. And so it's the same kind of thing when we look at a testing scenario. We need to verify that the technologies really work. And so of the clients that we have, I'll talk about it actually on the last slide, about 2/3 of our clients are technology companies. And so our role is to verify that those technologies work. Sometimes they do great, but sometimes they don't do quite as well as the salesperson might lead on to. The last one is a quote from Tillman, and I had to kind of paraphrase it because he had a whole paragraph. But basically, he calls it the 95-5 rule. And the context is success is based on the 5% that you really do. And so if you have a business, and I know a lot of you are operators, but in your business, it's the 5% that you do that determines really how successful that you are. And so if you look at your budget, if you allocate, I'm not necessarily saying you advocate 5% for full-scale testing, but if you take 5% of your overall integrity budget and you allocate it for validating models and doing those kind of things, I think you'll be amazed to see the benefit, the leverage that you get. Okay. So one of the other things about me is I love acronyms. And I started it when I was in high school. I remember in chemistry I'd make acronyms up to remember things like diatomic molecules, things that are completely useless today, but they were really helpful when I was a sophomore in high school. And so just over the years to help me remember things, I've made up acronyms. And folks that have had the misfortune of working with me know that they've had to hear some of my acronyms, and this is one of them. And so what we've got here on the screen is we've got 4 elements. And I also like my acronyms to be short so I can remember them. If it's probably got more than 6 letters, I'm probably not going to remember it. So basically we have ICAD. And so what I've drawn here is, being an engineer, I like graphs. And so I've got the risk level on your y-axis. And then on the x-axis, we have increased knowledge. And so I'll just kind of walk you through this process. I think the vast majority of you on the call today are pipeline folks. And in our world today, inline inspection plays a critical role. And some of you on the call maybe even work for ILI companies. I know a lot of you work with them, and they are our eyes and our ears. It's like getting in an airplane. I'm not sure if any of you are pilots. A pilot's always looking at his instruments, and to a large extent, the ILI companies are the instruments that we have when we're flying pipelines, so to speak. So what happens is we do the inspection, we collect data. Today's tools versus when I started working 27 years ago, it's a whole different ballgame. We have a lot better technologies. These ILI companies every year are continuing to advance technologies, and to a large extent, they're developing because you're challenging them to do things. We're doing a really neat project right now, and we're challenging the ILI companies to measure things that they haven't really measured before, certainly to a level. So this is where it starts. Then the next process is you categorize the defects. And so whether you've got corrosion or a dent or selective seam corrosion, stress corrosion, cracking, you have a bin, and all these things fall in these different bins. And you know as well as I do, if you've got a plain dent in a gas pipeline, you treat it completely different than you do low frequency ERW in a liquid pipeline. And so that categorization is very important. There's a lot of human interaction that happens at that place. Eventually, and Christopher DeLeon did a great presentation at PPIM this year, eventually with AI and us doing a lot of machine learning, we're gonna automate that process. But at this point, it's still very human intensive. So what happens is, you know, you look at my curve, I feel like I'm talking about the weather here, but you look at the trend that goes down, that's the world that we live in. That's the assessment. We have other companies in some sense that we compete with. I want to be Switzerland and get along with everybody, but you got folks like Ted Anderson, who's certainly the well-recognized fracture mechanics person, Sergio Limon. You've got the modeling side of it, and you do FEA modeling. There's a lot of companies that do that. We even do that. And so you can do the modeling side of it. Why we're here today, though, is to talk about the full-scale testing part. So what happens is, the more I know, if you look at that tagline on the bottom, the more that we know, the less risk we're required to take. And so what happens is my knowledge increases with information from models, information from testing. I'm able to take a higher level of risk because I understand more about how that pipe's going to behave. And then I get all the way, so we got ICAD, I'm going through I, C, we've talked about assessment that involves modeling and testing. And at the very end, I determine what I'm going to do. And I've spent most of my life working in the CAD side, okay? And I'm learning a lot more about the I. That's the fun thing about engineering. Even at 51 years old, I feel like I'm still learning like I did when I was a younger engineer. I just got a little more gray hair to go along with the learning process. But the last part is the determination. And it's not overly complicated because we don't have an infinite number of options available to us. But one of the options that we have is we can leave it in service. And to a large extent, I think there are a lot of features as an industry that we go out and that we look at that if we knew more about how they really were going to perform, we might not even go look at those. And so one of my goals, and I realize right now with the price of oil being hovering around zero, which is unbelievable. I feel like I'm in a bad movie sometimes with a lot of things right now. But we need to be very efficient. And I know as operators, you're going to be thinking about things. How do we save money? If we drive that curve down like I'm showing right here, we can save a lot of money. And I'm not necessarily just talking about doing less digs, because I think that's a dangerous mindset to get into. But to do things more safely, more efficiently, and more economically, I think is a good approach. And so the options you have, you leave it in service, okay? You excavate and you look at it and decide, do we really need to do anything? You can repair it or you can replace it. And one of the things that I think a lot of you that know me, I've spent almost all of my career working on composite repairs, got my PhD in it. I'm still actively involved in that. I really like it. I think it's great technology. I'm really proud of our manufacturers who've made big investments. We're continuing to do things in terms of leak repair and reinforcing cracks that 10 years ago we weren't even talking about. And so we've got a lot of options on this determination side that, that we can explore, and we're going to talk about some of those today as well. So hopefully no one's fallen asleep yet. It's a little early this morning. So this is the goal in testing. There's a lot of text on here, okay? And, the goal is not just to destructively test things and blow it up. Although I'll admit it's an exciting day to come in, and we blew a couple of samples up yesterday, a lot of energy. We're going to talk about safety. Safety is a huge thing for all of us. The pipeline industry, we eat, sleep, and breathe safety. It's one thing to operate a pipeline safety, but those of you who've been in our test lab, if you were there and we are doing a destructive test, we spend a lot of time thinking about containment and safety and energy levels in a way that I don't think a lot of the industry really has exposure to. So I've got two equations, and we'll talk about those here in a minute. You know, the goal in testing is not just to test stuff. And as someone who likes to test, it's easy for me to get excited about it, but I realize I'm not the wheel or the gear, I'm just a cog. And our goal is to make the models very, very effective. And so this last one here, very simply, the goal in testing is to help you more effectively make integrity and operational decisions. So if our models are great, then we can control our risk and we can go do things. So I kind of made a list, and we'll make this PowerPoint available for you. And I know I'm going to follow up with some of you, and we'll talk about these things. But as I've kind of been preparing for the past couple of weeks, I thought about, you know, what does this process look like? So the first thing that you do, and as operators, this is the world you live in. You run your tools, and you identify that you've got features of interest. And then the second thing is, once you give us a call and say, Chris, we've got selective seam corrosion, we've got a dent in a girth weld, we've got a girth weld that's going to potentially be subjected to bending loads, we spend time talking to you about the test. How do we plan it? And if you remember a couple of slides ago, I had a whiteboard up, and it all starts with a whiteboard. So much of our life on the testing side involves a group of engineers and technicians getting together in a room and just running over different scenarios. So a really big test, we spend a lot of time planning things. And so this second bullet is super important. And I will admit, you know, I'm president of ADV, but we've got a team of people that we trust each other. And I lean very heavily on Corey Duncan, who's our lab manager, and Chantz Denowh, who's our senior engineer. And I really rely on their expertise. And we, before we do anything, we have a lot of discussion. So this second bullet is really where the rubber meets the road. And then we've got a choice between whether we're going to be creating features, and that means we put a dent in a pipe, we put an EDM notch to simulate, to start a crack, or do you provide to us features that have been removed from the field? And so that's a big decision. It's very difficult and expensive to get features, and sometimes you don't get what you want. And so we spend a lot of time in the lab simulating and creating defects. And in our case studies, you will see that we do a lot of that. Then you got to figure out what the loads are. For the most part, it's relatively easy to test pipe because we're looking at pressure. But every now and then, you get a situation where you need to put tension load, and you may need to apply bending load. And so sometimes we have to build frames in order to do those things. And then we design the test program. One of the things that we spend a lot of time doing is we talk about instrumentation. And so I've really relied a lot on Chantz and Corey and the guys in the lab to make sure that the instrumentation that we have is working. And you've got data acquisition systems that are collecting all the data you need. So that's a big part of it. Then you conduct the test, you record the data. The worst nightmare that you can have is you start a test and you forget to record data. And I'm happy to report in our, you know, a little over a year of doing testing, we haven't done that. Most engineers have a horror story when we've done that. It's kind of like working on a big report when you were in college and you forgot to save it and you lost everything. So it's kind of the equivalent. So, you know, we check each other and make sure we're recording data. Then if we've got models that we've been asked to validate, and we basically do the comparison of the data that we get experimentally to the data that we get in modeling. And then the last thing, which is oftentimes the reason that you hire us, is we get fed into your integrity models. And so this is kind of a 20,000-foot overview of how we use testing to basically plug into your integrity management programs. Okay, so I do have a little safety moment. I saved it after we kind of had gotten started. So as I alluded to earlier, we spend a lot of time talking about energy levels. And I think most people don't have an appreciation for energy levels. If I told you something was 1,000 foot-pounds, you're like, well, what does that really mean? Well, the way I explain it to people who aren't engineers, I'm like, imagine taking 1,000 pounds and lifting it up 1 foot and dropping it. Okay, I can understand that. And so when you get into blowing pipe up, you calculate relatively high energy levels. So we blew some samples up today. Actually, there were 12-inch. I do a lot of testing on 12-inch pipe. It's easy to do. It's easy to manufacture. And so we blew some pipes up yesterday that blew up at around 4,000 PSI. So there's an equation here, and there will be no test afterwards, no pop quizzes. But this is an equation to calculate the energy in a vessel pressurized with liquid. And what you notice there is, without going into a lot of terms, the beta term is the compressibility of water. So if you did hydraulic fluid, it'd be a little different than water. P is the internal pressure and V is the volume. So what you notice is P is squared. So if I double the pressure, the failure pressure, okay, 2 squared is 4, so I've increased the energy level by a factor of 4. So we spent a lot of time watching this. So the pipes that we blew up yesterday had a fair amount of energy. They make a boom. It doesn't shake the building. It's around 20 or 30,000 foot-pounds. Now, once again, going back in the context, that's equivalent, if I'm at 20,000 foot-pounds, that's the equivalent of taking 20,000 pounds and raising it up 20 feet in the air. That is a lot of energy, right? And so that's the thing, you wouldn't want to be under it. It's why when we're lifting things, we don't stand underneath them. Because to be honest with you, even if you take 50 pounds, okay, and you drop it from 20 feet, that's a lot of energy. So that gives you a context of what we're talking about. Now, the reason we're doing this is, what's the difference between liquid and a gas? And probably half of you on this call are gas operators, and you understand the energy that's associated with a gas pipeline failure. So what we did was, the equation you have to use for gas, and if you remember this from thermodynamics, and most of you probably like me has forgot a lot of your thermodynamics, I was glad to do that. That was not my favorite stuff in school. But you run through this, and it's the same basic equations, but the reason that gas has so much more energy is it's compressible. And you know this if you've blown a balloon up or you've aired a tire. Gas can be compressed in a way that liquid can't. So what happens is you keep putting a lot more energy into that, and that energy is stored. So for the same basic test that we did yesterday, where we were at about 20,000 foot-pounds, if we had done that with gas, we would have blown our building up. And so that's got about 5 pounds of TNT. And I think a pound of T is 1.5 million foot-pounds of energy. And so it's a little easier. Not that I've ever blown stuff up with TNT, but that kind of gives you some context. So that's our safety moments. A little math. If you got kids at home right now, you're probably having to help them with math homework, and probably realize our teachers all need to get a raise next year because we're having to do stuff we haven't done in a long time. So, because we can't go to Waller and you can't come out to see us, we're going to do a virtual lab tour. So I love some photos here, and one of the ones I really like is this top left one. So we leased a building back in October of 2018, and it's kind of Corey and Wendy and I and a technician, and then Chantz Denowh and John Rickert came on. So when we started in 2019, this is what it looked like. I don't have a picture of it today. You'll see some images on the inside. It is completely filled up. We're trying to figure out how we can move things around all the time. So for me, it's kind of exciting to have started a business and just to see how it's grown. And I think we've had a lot of fun. A lot of you on the call today, you're the reason we've been able to grow this business. We got about 4 acres. I think I got this off Google Earth, and you kind of see we've got a lot of area. Back in the back, Rosen has loaned us their pull rig, and so we've been working on a project and pulling some things. So we've got a lot of space. We've got kind of a grassy area here where we can bury things. We did a project for TC Energy where we buried some composite samples in the ground. So we've got room to do stuff, and when you're doing testing, you really need room. You can't just do things in kind of a small office building. So it served its purpose well. So one of the first things that we had to do was, we're doing pressure testings. We had to figure out where we're going to do these things. And when we moved into our building, there was an area inside the building where we looked at possibly putting some pits in. And those of you who've been around for a while, you've got a couple of options. You either contain it above ground or you contain it in the ground. And after some debate, we just decided it was better to build kind of above ground bunker. And so this is our box, our containment box. And we basically we pressurize. I think the largest sample we've done is 36-inch diameter, is about 25 feet long. So we've got the capacity to do this. If we need to get into longer samples, okay, then we can build a bigger box. But for the vast majority of what we've done, we've been able to do it. We've had some pretty high energy levels in there, and we spent a lot of time running calculations. Corey Duncan did a great job designing this, and it's worked very, very well for us. One of the other things, and I talked about earlier, the vast majority of what we do, probably 90 to 95% of what we do, just involves pressure. So we're pressurizing samples, we're pressure cycling, but on occasion we're asked about putting external loads. And we've got a project right now we're doing with PRCI looking at large standoff magnetometry. So we're going to build a facility outside that's about 120 feet long, and we're going to displace the pipe to simulate land movement so the LSM technology can go over the pipe and look for displacements and stresses. So we had two projects early last year that came along, and the operator said, look, we need to put some bending loads. And so one of them was looking at girth welds, another one was looking at wrinkle bends. So, you know, kind of in our world, we're starting with a blank whiteboard, if you will, since we've used that. And we're like, okay, let's design and build a load frame. So Corey and Chantz are primarily the brains behind this, and so we basically have an I-beam. I love Corey's design because we've got two I-beams, and we drop the cylinders in the middle. So what happens is it keeps the sample relatively low. A lot of the work that I did before in places I've seen is you lift the sample way high in the air, and it's a little bit more of a safety hazard. So I like Corey's design. And so you load the sample in between these two cylinders. These cylinders will do about 460,000 pounds each. We displace it. Chantz wrote a little algorithm. We actually can do fatigue loading. So if you got a situation where you're concerned about the pipe moving back and forth, you know, Chantz and our technicians have got a program where we can simulate that displacement. And a lot of times it's a little bit more money to look at fatigue, but the benefits that you get looking long term, it's extremely valuable. And I had to stick this photo down in here. You know, I'm kind of a kid at heart. I love toys, and so we've got a 3D printer, and a couple of our guys have gotten really good at using it. So anyway, Corey 3D printed a model of our load frame. So I know once we get out of the house and we go to shows, we'll bring that with us to shows. It's kind of hard to load this thing up in the back of a pickup truck. But we can take it with us and people can see it. The other thing about the 3D printer, a little plug for kind of where I see things going. Atul Ganpatye started with us. I feel like he's been with us for a couple of years, but he started in February. And there's an area called additive manufacturing where we're as an industry really looking at manufacturing pieces, okay, using a 3D printing process, doing it with metals. And so I'm really excited. That's kind of a forward-thinking concept that we're looking at ADV. The other thing I like is sometimes in the lab you need to build a little bracket to hold this or that. Historically, you'd go out and you'd bend some steel or you'd make it out of wood. Now the guys just design it in SolidWorks. They fire it into the 3D printer and they print it out. It's got threads in it. So I've been really impressed with how our engineers and technicians have been able to use that 3D printer to basically make things that we use in the lab. So one of the things that we've done, we did a project earlier this year, we went down to, and just I want you to think about this for a minute, minus 51 degrees Fahrenheit. And that is really cold. We live here in Houston, and when it gets much below about 60, I start getting cold. So when you get to minus 51, that's really cold. Well, we needed to do a pressure test, and so Corey designed for us a box, and he and Chantz got together and figured out how to basically build this box to cool it down. I took a photo as we were opening a box. We basically insulated a Connex container. This box here does all the structural reinforcement. We slide it out. It's on rails, and we load the sample in there. We've got a box, has a lid. We bolt the lid down. We slide everything in. And then all of this equipment here, okay, liquid nitrogen, we've got a large tank, we start cooling samples down. And so I was really impressed with how everything came together. I talked about earlier safety. And so one of the things that we do when we design structures containment, we want to make sure they can withstand the energy levels. And so as you can see, it's a big box. It has the capacity to absorb a lot of energy. and then we have the ability to slide this thing in there and cool it. We've also run some elevated temperature tests. I've got a little note here. We test a composite up to 60 C, and so we got a pretty wide range. We can go higher than that, but most of the reason we're doing any elevated temperature work, it's to focus on the composite repair technology. So that kind of gives you an idea of our overall capacity. One of the things I've enjoyed doing, those of you that know me know I love joint industry programs. I kind of keep a running tally. I think done about 20 JIPs. The very first one I did was back about 15 years ago on my PhD, and we get a lot of industry leaders and thought leaders together, and we get technology companies. So this is a great example of a JIP that's been very successful. We were approached by Chevron to do a project looking at spoolable pipe. And so we reached out to a group of operators and have had an incredible response. And then we reached out to the spoolable pipe manufacturers. So we designed and built these load frames. And the next slide, I'll show you kind of what it looks like. And we started this project in around December of 2018. Had a meeting here in Houston, got a group of people together, kind of framed out what the test program was going to be. And it's been wildly successful. I was hoping that we'd have 3 or 4 operators and 3 or 4 manufacturers. I think last count we had 6 operators and 8 technology companies. So it's really grown. We've really learned a lot. Earlier this week we were doing some burst tests, and things are looking really good for these technologies. And this is kind of a little schematic of what our system looks like. So we'll take the spoolable pipe and we displace it vertically. And so what we're doing is we're putting a bending moment on this connector section. And we basically pressurize them for 1,000 hours. We do 100,000 pressure cycles, and then if they survive, then we'll do a burst test. So anyway, this is information that we've actually presented at the API 15S meeting. If you're interested in learning more about this, please reach out to me, and we'd be glad to visit with you. But as I said, it's a great example of industry working together. The power of JIPs is a couple things. One is you get a lot of good thought leaders within the technology companies and the operators. And when you get a lot of really smart people, you're going to come up with some really good concepts. Now, I will admit, as someone who's organized a lot of JIPs, it's challenging at times to manage them because you've got a lot of smart people, and smart people have opinions. And we certainly know today there's lots of opinions floating around. Well, engineers also have opinions. And so there's some psychology involved in us all figuring out how to work together. And then the technology companies, it's a great opportunity for them to kind of showcase their technologies and to demonstrate what they can do. And then the other part, which I think is really important, especially with the price of oil where it is, we're going to be very cost conscious. And so you can come into a problem or a challenge that you have, and you're like, I've only got $50,000. You call us, and we work with you, and we go out to industry, and that $50,000 can become a $500,000 JIP. I think even the folks in Wall Street would like that kind of return on investment. So I think it's a great way to solve challenging problems in an economic fashion. So one of the other things that we did, and I will admit when we started 2019, I did not think that we would do this, but we bought a little Tenius Olson machine. It'll do about 120,000 pounds. It will do cyclic loading. And so one of the things I want to do this year is we're doing work with a company, and we're doing some composite work, is to do some fatigue testing on composite materials. It's relatively automated, but we can also do tensile samples. This is actually a wrinkle bend where we're doing some high strain, low cycle wrinkle bend testing that has worked out really well. So anyway, that's just kind of an example of the kind of things that we can do. The nice thing is if we need to do a quick pull test, we've got the facility to do something like that, and we don't have to wait to send it out. So one of the first areas I got involved in the oil industry in 1993 was looking at dents. And I'll admit, when I was at A&M, I had no idea what a big problem dents were in the pipeline industry. And there's a lot of work. There's some great work that's been done by PRCI looking at dents. It's a big part of our industry. Everybody has dents. How do you assess them? So we've got a little rig. This is the small dent frame. We have a large dent frame. We can dent pipe, I think, up to 36 inches. And we basically put a dent in. It's like my monitor went to sleep again. Pause just for a second. So I'll keep talking. Yeah, on the live stream, we're having problems. I think our computer keeps. Let's see if I can do this. So I'll keep talking for those of you who are on the WebEx. So basically what happens is when we go to create a dent, we simulate what happens when that dent's installed in service. And so we'll put pressure in the pipe, and we push the indenter into the pipe, and we hold it in place while we're pressurizing. And then what happens is through that process that we create a very, very severe dent. And the end result is you've got this very severe, you got a lot of area, you got a very high level of plasticity on it. And so we'll take that dent and we will wind up pressure cycling it. Most of the time we don't do burst test. And what happens through that process is we find out how's the dent really gonna perform. And I apologize. There we go. We're having some technical difficulties, but we're gonna figure out how to do that. Wendy, how are you looking on your screen? Everything okay?
It's coming up.
Okay. Apologize for this. Okay, here we go. So I was talking about dents. We've done a lot of dents over the years, and we've learned a lot. But the interesting thing is we're continuing to learn more. And we'll put a strain gauge on it, and we will measure the strain. This is actually a fatigue failure that we get. If you know anything about dents, plain dents, the reason that it fails is it fails due to fatigue and due to cycling. If we were to do a burst test on it, the first thing that happens is we basically just pop that dent out. So we're going to continue to do more. What makes dents often damaging is the interaction with mechanical damage. And this is kind of a busy slide. I just grabbed a bunch of photos of instrumentation around the lab. Data acquisition and instrumentation is so important. And it's an area of testing that doesn't get a lot of attention. But if you don't have good instrumentation, you can't just blow things up or pressure cycle to failure. You've got to get information from that. So I've got a couple of photos that show our data acquisition system, some of our instruments. And sometimes we just build things. We'll take a LVDT and we'll hook it up, and it allows us to measure displacement or rotation. And there's a lot of creativity that goes in that. If you have a mechanical engineering degree, odds are you had some kind of controls class. And so I've been really impressed with our guys and learning how to do controls and be able to not only collect the data, but sometimes use that information to control pumps and load cylinders and those kind of things. So sometimes you just get a big mash of data, and this was literally a data set that we got. And so Chantz and I were working on a project, and we just looked at this thing. It's almost like looking at an ink blot. It's like, what in the world do you do with all this stuff? But to Chantz's credit, he spent several hours and kind of went through things. And basically, one of the things that we figured out, we had strain gauges around the pipe, and we were pressurizing it. It's not rocket science. It's PR over T is the hoop stress. But we had gauges all the way around, and we were getting some really weird readings. Like, 90 degrees of strain was different here. And if you're doing anything with large diameter pipe always has some level of ovality in it. And so what happens when you got ovality, when you're pressurizing, and I'm exaggerating a little bit here with my hands, but you create an ellipse, and as you pressurize it, the strain changes around the circumference of the pipe. So we spent, a couple of hours and then eventually a couple of weeks processing through it to the point where we felt like we understood what was going on. So it's not just collecting data. Sometimes there's a real challenge in knowing what to do with the data once you collect it. Okay, so let's run through some case studies. We're about 39 minutes here. Case studies are extremely powerful in terms of telling the story. So one of the areas that's getting a lot of emphasis right now is cracks. Crack management. Our ILI tools are finding things, and they're seeing cracks that 20 years ago we didn't even know were there. So the problem is once you find them, you've got to do something about it. So there's a lot of interest in looking at the performance, but there's also a lot of interest looking at the inspection technologies. And so this is a project that we did. An area of great interest right now is low frequency ERW pipe. And so we put some EDM notches in. This is a EDM notch installer. And there's a little electrode that goes down into the pipe, and it basically creates a notch. And doesn't sound very complicated, but it's an extremely detailed process. You've got to be spot on for a couple reasons. One is what you notice is we've etched this surface here, and you can see this little white line. we're looking for an area where the ERW seam comes together. You've got to install that notch right in the middle of that. So we are mechanical engineers. We're learning a lot about metallurgy, and it's very important as we go through that process that we make sure that we've got that information before we start putting notches in pipe. And these are just some tests. So what you can see here on the bottom left is there was a crack, and we cycled it to create a crack at the base of that notch. And I'll admit, when I first started doing a lot of this work 6-7 years ago, I didn't fully appreciate. I remember Ted Anderson and I having a little discussion about that time. He's like, look, Chris, notches are not cracks. And when you section this, you know, when you send the electrode in there, this thing is like 10,000ths of an inch wide. It's very, very narrow. We try to make it relatively sharp at the bottom, but you push it in, and then you take a cross section of it, you put it under a microscope, that is not sharp at all. But when you cycle it, what you notice is we get that crack. That crack is sharp. So now if we did a burst test, okay, we're really testing a crack. And so what you can see in these samples here, there's a couple things. One is the left image, you can see the fracture. And if I show this picture to you, and you've been in the pipeline industry any length of time, and I said, why do you think it fell that way? Your response would be, because it's in a low frequency ERW seam. And that's exactly what happened. So we had a notch, we pressurized it, and it ran the whole length of the pipe. If we tested with gas, we would have run all the way through the end caps. And so when pipelines fail and they're under high levels of pressure, this is what happens potentially in a low frequency ERW seam if you get a fracture to run. On the right side, we tested a composite system. This is actually a Millikan or CSNRI's Atlas carbon epoxy technology. We've tested it a lot, reinforcing cracks with extremely good results. And so we had the same defect there, and what you notice is the fracture initiated outside the notch crack that we had created. So just a great example of how we're able to take real pipe. This is pipe probably from the mid-1950s, put an EDM notch in it, do some pre-cycling to get cracking, and then we test it to simulate what's going to happen. So the beauty of this is this went into this operator's integrity management program, and they had confidence in understanding how the feature geometry in terms of length and depth affected the pressure capacity of their pipeline. And in general, what I have seen, and as engineers, we tend to be conservative, which is a good thing. It's the reason wings don't fall off airplanes and wheels don't come off cars. We tend to be very safety conscious. When in doubt, one of my favorite sayings in the oil industry is, when in doubt, make it stout using something you know about. And I heard that from an old metallurgist years ago, and it's a great philosophy, but sometimes it's possible to possibly be a little bit overly conservative. So that's the whole gist of this program that we're talking about today. Let's make sure that we're being safe, but let's make sure that we're doing that based on some scientific rigor as much as we can. So one of the other things that we're doing, I mentioned earlier, we're not only testing pipe, but we're also looking at technologies. And so we're looking at computed tomography. There's a couple of companies that do this. Probably one company that has kind of taken the lead, at least in the pipeline industry, is Inspection Associates, also co-owned by Sonomatic, and some of you know both those organizations. So James Medford has developed a technology, and I've got a photo of it here, and this CT technology actually goes around the pipe, and it creates a three-dimensional image of crack-like features. And so we did a little project for him. We took some 12-inch pipe, we put some EDM notches ranging from 10 to 40%. We did some pressure cycling to create cracking, and then we sent it back over to James and we let him make some inspections, and then we got his data back and we broke all of these features open, and we did kind of a side-by-side comparison. If you're really interested in this, the last slide I'll have my email address. I think a lot of you probably have it, but shoot me an email, and we've got a P-Pen paper that we presented back in February where we talked about this program. So there's a lot of data in there that gives you an idea of how this technology works. PHMSA and PRCI are also sponsoring a project. It's the NDE-2-11 project, and we're creating a lot of features and going to be doing a lot of inspection work. So I think it's great to see the industry kind of moving the ball forward as we look at advancing these inspection technologies. So what we did was we put weldable strain gauges across the notch, and what that allows us to do is monitor the crack opening up. And as it opens up, what you see is the compliance in that notch changes and the strain really starts going up. And so we did a project with James Medford working on this. We did a big project for Rosen that we also presented a paper at PPM. So, we developed some expertise on this in terms of really determining when do you stop. We've got some other things that we're working on as well to really kind of help us understand where are we in terms of how far the crack's propagating. So I think there's just a lot of opportunities that we have as an industry really to advance this. You can see in our green box, we've got the samples there, and we'll pressure cycle, and then we stop at a certain point. So once you do all the cycling and you do the inspection work, then really the fun starts. And so we basically open these up. And if you look right here, and those of you who are live streaming this, you can see us, but visualize my finger looking at the notch area. And so the notch is relatively straight as it goes across there. And then as you cycle, and if you've done any fracture mechanics work, we always assume that the fracture has an elliptical shape. This is a textbook example of what that fracture looks like. And so these are two mating surfaces that are broken open. And as we cycled, it grew. We obviously stopped it, okay, so that James would be able to make the inspection work. And so we break it apart. If we had continued cycling, that rusty area would have gone all the way through, and we would have had a through-wall defect that would have developed. On the right side, you can see what I'm calling the transverse view, and that section right there is looking down the axis of the pipe. And so you can see the EDM notch, and you can see how much our crack grew in that process. So these are basically the same image. We just split the notch in half, and in one of them we broke it apart, and the other one we looked down the axis of the pipe. So, I like that we're doing this. It's kind of something, we may not be the only people who have invented this, but when we first started breaking these notches open, to me it seemed a waste to have to break the whole thing open. So by sectioning it, we're able to get two different views, which give us two pieces of information about the notches. So John Rickert, one of our young engineers, has really done a good job learning how to do this, and it's been very, very valuable for us. So these are the images on the right that we get from James. And so he's running his inspection technology that is called computed tomography, and you can Google it. There's a lot of, it's used in other industries, but I think for the pipeline industry, it's got a lot of promise because of the accuracy that you're able to get. What we haven't looked at is hook cracks, that they don't just run radially, they actually curve away from a radial plane, and it's practically impossible to get that with conventional NDE technologies. Well, with the computed tomography, because you get a three-dimensional image, you can see that kind of morphology of the crack. So we're just doing a side-by-side comparison. It's kind of like Consumer Reports. We're comparing all the data. So what you notice here in this plot is the actual depth is what we measured base once we cracked it open compared to the CT measured value. And a perfect set of data, it lines right on top of that line. And I could have put error bars and those kind of things on it. But my observation, based on a very simplistic view of the presentation of the data, is it's worked very well. There's a lot of good accuracy that we're seeing with that data. I think in the PRCI project, we're probably going to be looking at probably in excess of 90 features. So the more data that we get, the better we're going to find out. What I found without going into a lot of depth is the accuracy is higher on the more severe features. And I think probably most NDE technologies, that's the case. So this is case study 3 of 4. This is some recent work that we've done with TC Energy, and we are going to have a paper at the International Pipeline Conference. I'm really hoping that we get to have it, hoping that our leaders up there who are running IPC, Pat Veith, and some of the other gentlemen and ladies. It's a challenging time trying to figure out forecasting September, October, what we're able to do. But this is a paper that will either be presented in person or we'll be doing it online. And so this paper talks about a study that we did with TC Energy looking at repairing severe corrosion and leak defects. And it was a great study, and we'll be presenting this information. I'm really excited to see how we're pushing technologies. And this is a good example of that. I don't have a lot of detail. I have kind of the major categories. So we took very thin wall pipe, 156 inch, about 4 millimeter if you use SI units, which most of the world does except for Americans. We're stuck in our English units. And we created 85% corrosion features in it by machining. And to be honest, I was really impressed with our machine shop that they could even do it. It's very challenging to get that kind of accuracy. So if you think about it, we've got a 15% of a 0.156-inch wall, very, very thin. And so some of those we drilled holes in them. We did nitrogen gas testing for 90 days. We did some elevated temperature testing just to simulate how these composite systems would perform. The Canadians run to a higher pressure than we do for the most part, so they run up to 80%. So we really pushed the limit on these technologies. We also looked at flash rust and not having ideal surface prep. And we did burst testing and cyclic testing. And these are just a couple of images. This is the buried pipe in the ground before we put the soil back on. And these are just some schematics. And we had two companies that participated that we'll talk about in the paper. One was Western Specialties Composite Sleeve, which is a steel half shell that's glued on the pipe. I've tested that technology for probably over 10 years and have always gotten extremely good results. And it's an alternative to welding. You're adhesively bonding that steel sleeve. So it does real well in leak repair because as that corrosion wants to bulge out, you've got steel pushing it down. The other technology that we looked at, and it seems like we're running a lot of tests with these two companies, is a CSNRI's Milliken Atlas carbon epoxy system. I talked about it earlier. It's been very successful in crack reinforcement, and both those technologies did very well in this program. So I'm very optimistic. Very bullish about the future of using these kind of technologies to really push the limit for us. And the last one, because I don't have a lot of time, is a PRCI project that we did. Very, very large project. Large in terms of scale, large in terms of scope. And David Zhu with PG&E is kind of I call him the godfather in this. I actually think he's on the call this morning. And the idea is looking at these pressure isolation technologies, running them down through the pipe, remotely setting them. So just envision you've got an area that you need to repair. You run these tools, okay, and you set one here and you set one here, and they lock in place, and you're able to have a high pressure on each side, and in the middle, you can bleed off the pressure. So it's also like a freeze plug. It's a very high-tech freeze plug, and it allows you to possibly replace that section. Maybe you're working on a valve. So it's really neat technology. So one of the concerns, these are used offshore a lot. One of the concerns onshore was that we would have very high pressures or very high stresses, created due to the elevated stresses because we have thin wall. And if you've done any offshore pipeline work, offshore pipelines tend to be very, very thick because of the concerns of the compressibility of the deep water environment. Onshore, we tend to have thinner wall. And so these tools come in and they set. And so we built a bunch of FEA models of this. This is kind of a little schematic. So you have a high pressure side, a low pressure side. As this tool sets, it expands in place, and it has to lock itself in place so it creates stresses. So we've got some images here, and if you've done any FEA, red bad, blue good. It's pretty simple. And so you've got some areas where you have some elevated stresses, but to me, the thing that was very beneficial in this, and I'm going to give David a lot of credit, we started off, we did FEA models to try to understand it, and we had 3 technology companies who were extremely helpful. We had TDW Stats and PPIG, which is a pipeline pressure isolation group. All 3 of those companies, they contributed financially, they contributed their time, and they contributed their expertise. And what we found was the models were actually very accurate relative to what we measure with the strain gauges. And so this is one of the isolation tools. So we drop it in our little test fixture. It locks in place. We pressurize one side, and on the other side, we don't want to see pressure. And you can see we're putting a lot of strain gauges and we're measuring it. And that, if you remember the image I showed earlier that had a lot of crazy data, this was actually from that project. And so we went through, we processed, and we determined what the stresses were. So just a great example of how you can use analysis and testing. And then we eventually went back and we sectioned each of those pipes because the concern was possibly creating damage. And what we found was there were some superficial marks that were really below the mill tolerance of the pipe. So from my perspective, we could possibly do some additional work, but I think certainly for lines that don't see a lot of aggressive pressure cycling, I don't think that we need to be, overly concerned based on the research that we've seen. But the beauty in this, there were a lot of questions up front that people had about these technologies that today we've got the answer because we did the full-scale testing. And then we eventually took the FEA model, sharpened it a little bit, got the accuracy a little bit better, and we built an Excel tool that's now you can go in and say, I've got a larger diameter pipe, can I or can I not use this tool? And so we developed a very useful program for PRCI. And once again, David was kind of the godfather and really provided some guidance for us. So kind of the last thing, talk about the CT validation. Cracks continue to be a big area that we're concerned with. And so these technologies like the pressure isolation, computed tomography, they're allowing us to really look at where the technologies are headed. So kind of wrapping it all up, Wendy's back in the back telling me I've got about 2 minutes, so I'll wrap up this presentation. I hope it's worked well for you. As I said, the live stream was a little bit of an idea that we had earlier this week, and fortunately, due to my very smart daughter, it all came together. So kind of some closing remarks. Last year I've got a little spreadsheet that has all the companies that we did work for. We worked for 43 companies, and as I said, the vast majority of you on the call today are operators. And we work for 15 of you, and we appreciate you working with us. We appreciate your contracts, folks, not making MSAs overly complicated. So overall, just been a great process. Obviously, we started off the presentation today. Testing is extremely valuable in terms of helping us face challenging decisions. And we've got a couple of projects we're working on right now with you as operators. And there's a lot of pressure that you're under. And we just want to kind of come alongside you and use the capabilities that we have out in Waller, Texas, to help reduce possibly the stress that you have when you have to make these decisions, but also just to come alongside you and expose you to some of the things that we're doing. And it's that third bullet is testing validation. We as I said, about 2/3 of the people we worked with last year were technology companies. And the next to last bullet, we live in a regulated environment, and PHMSA likes performance-based work, and that's exactly what we're doing. So anyway, my last bullet there is give us a call. We're here to help you. We've worked with a lot of you, and Chantz doing a great job. He's actually working this morning on some projects, so I told him I'd do today's presentation. But we appreciate your time, and if you need anything, you got our contact information there, and we look forward to hearing from you. Thank you very much.